Hello, everyone, and apologies again that I'm rather under the weather and was not able to make it in person today. But as you can tell from my basso profundo voice at this point, probably for the best that I don't expose you to whatever I managed to acquire on my conference. But today we're getting into the very last topic of our course, which is a rather exciting one, and it brings us in some sense back to an idea that we encountered at the very end of our first third of the course, the idea of linear regression. So we're going to be looking at relationships between a numerical explanatory variable and a numerical response variable. But on the other hand, it's also going to add an interesting wrinkle to what we have been looking at recently with respect to analysis of variance. So we'll begin today by considering sort of a big picture question, which is the idea of explanation as a form of error reduction. In other words, the idea that when we have a numerical response variable and we're trying to make guesses about what the value of that variable might be, we're interested in how well some other variable, our explanatory variable, can explain why the response variable changes. So that's our kind of first major topic, and then we'll see how that manifests in both analysis of variance, what we were talking about last week, and linear regression, our topic for today. And then finally, we'll get into some mechanics of doing inference with respect to linear regression, in particular, looking at our kind of two categories of inference, doing confidence intervals. In this case, we're making confidence intervals for the slope of a linear model. So, as we remember, and we'll see again, the slope is the rate of change in the response variable as the explanatory variable changes, as well as hypothesis testing, because we're usually interested in questions like, is that slope different from zero? In other words, is there in fact a meaningful relationship, or do we have evidence to believe that there's a meaningful relationship between the explanatory and response variables? So that's on deck for today. And here I'm showing stuff that we've all seen before. This all mostly comes from our work last week. This is our anorexia example here on the left. So this is the data we're working with. We have, again, our 72 patients divided into three groups: control, cognitive behavioral therapy, family therapy. And last week we saw how analysis of variance allowed us to test the null hypothesis that all of those treatments were equally effective. And this here is our analysis of variance, or ANOVA table. As we saw last time, this is very convenient because it contains all of the sort of necessary numbers that we need to perform our calculations to get our F value, and then we either use simulation or our mathematical model, the F distribution, in order to find that P value up there. And one thing that may have been a little bit mysterious last week is where this name comes from, analysis of variance. Well, analysis of variance, that name, comes from the idea that we can decompose the total variability among all the observations that we've got into variability due to two sources. On the one hand, group differences, that is to say, an effect of group on excuse me, an effect of group on the response variable, and then everything left over. So this is what we called within group variability, or what a lot of software packages will call just error. But the idea is that the total amount of variability in our response variable, so in other words, all of the variability among all those 72 patients, can be decomposed into two sources. The kind of typical variability that we would expect to see between people in general, and then the variability that's a function of, or an effect of, which type of treatment they were assigned to. Now, once we have that idea, we can then ask, out of all of the variability in our data, how much can still be, how much can be explained by group differences relative to how much variability is still left over. And this gets us to an interesting number called r squared here. And what r squared is a ratio. It is the proportion of variability due to group differences divided by the total amount of variability in our data. And here we're quantifying variability in terms of the sum of squares. So this is this column here marked SS in our ANOVA table. And we can see here that, these are the sort of numbers that we need. This is where they come from. So we are interested in asking, all right, this is the sum of squared deviations due to group differences. And what we're doing is dividing it by the total sum of squares from both sources, which is given down here, this bottom line here, the total. And this number, r squared, is called the proportion of variance explained or accounted for by our explanatory variable. It's also sometimes called the coefficient of determination, and we'll see why in a bit why it's interesting that this is called r squared, because that'll come back again, remind us maybe a little bit of something we learned about at the very beginning with respect to correlation. So here's the calculation carried out with our anorexia data. So we have r squared here, and that's 615 divided by the sum of those two sums of squares. And this is the result, 0.136. And what that tells us is that about 13.6% of the variability among anorexia patients in our sample can be explained by differences between treatments. And the rest, so everything left over from that 13.6%, is left over. In other words, it's explained by other sources of variability, things like individual differences, sampling error, maybe measurement error as well. And just as an aside, I'll point out that especially if you are currently in or have recently taken Psych 101, you'll probably have encountered some examples of what are called twin studies. These are studies in which we compare, say, fraternal versus identical twins. And you may have heard on the basis of those studies that they're able to identify how much of a particular trait, like, say, intelligence or sociability, something like that, is related to either shared genetics or shared upbringing. And the basis for that number to say that, say, 40% of intelligence is heritable, for example, if that's not literally true, but let's say I use that as an example, that statement comes from this number. In other words, it comes from trying to partition the differences between siblings into those two sources of variability: shared genetics, shared upbringing. And we can use the same sort of calculation to figure out, all right, out of that total amount of variability between siblings, how much can be explained by the fact that they share genetics versus the fact that they simply share an upbringing. Now, as I mentioned, this concept of proportion of variance explained, or using an explanatory variable to explain differences in a response variable, is not limited to categorical explanatory variables like we've been dealing with analysis of variance. It extends into numerical explanatory variables, and that's going to be our main topic for today with respect to linear regression. So we're basically just making the switch from having, so in both cases we have a numerical response variable, and we're making a switch from a categorical, typically nominal categorical explanatory variable in analysis of variance, to now a numerical explanatory variable for linear regression. And this is kind of visualized here in these two different plots, where here we might use, say, a box plot to visualize the effect of a categorical explanatory variable on a response variable. But now in linear regression, we've got our old friend, the scatter plot. So we've got a numerical explanatory variable on the horizontal axis and a numerical response variable on the vertical. And the key difference here is that when we have a categorical explanatory variable, as we know, there's no systematic relationship between different values or different levels of the explanatory variable. All we're interested in is just, hey, are there differences at all? That's all we can say if we've got a categorical explanatory variable. In linear regression, there is a systematic relationship between different values of the explanatory variable because they're on a numerical scale. And so what we're trying to do is use that systematic relationship to explain changes in our response variable. Now, just to remind us of some concepts and terminology that we had when we dealt with linear regression and relationships between numerical variables way back in the first third of this course, you'll recall that we have this thing, the Pearson correlation coefficient, usually just written as R, that helps us to summarize the strength and direction of a possible linear relationship between two variables. And that's kind of a useful way of, as I say, kind of summarizing the qualitative features of that relationship. But then we can also take a deeper look and ask, well, okay, if there is, in fact, a linear relationship between those two variables, like we see here on the example on the right, what does that line look like? Well, that line is defined by an equation with two, as we say, coefficients. And on the one hand, we have an intercept, which is the value that the response variable would take when the explanatory variable equals 0. So that's where it intercepts the y-axis. But then the thing that we're going to be most interested in today is the slope. In other words, this is how much the response variable changes if the explanatory variable is increased by 1 unit. So if we make a unit change, a change of exactly 1 in the explanatory variable, how much would we expect our response variable to change? That's our slope. And you can think of it as basically the kind of the rate of change, if you will, the rate at which the response variable changes as the explanatory variable changes. When we first encountered linear regression, we used this example from Francis Galton, where he was interested in predicting the height of children from the height of their parents. And we found here that this was the equation that described that relationship. For each inch taller the mom gets, the daughter is expected to increase in height by about 1/3 of an inch. And as we talked about when we first introduced this, is kind of nonsensical, but if we could have a mother who is exactly 0 inches tall, this model says that her daughter would be 43.2 inches tall. So that's our intercept, and this is our slope. Now, I mentioned that we can use the same kind of concept of thinking about explanation as error reduction, just like we saw with analysis of variance, but now we can apply that idea to linear regression. So to do that, we can first count up the total residual error between observed values and those that are predicted by this best fitting line. Now, we remember that the best fitting line is the one that minimizes this quantity. It minimizes the squared residuals. So here are residuals, the observed value of y for a particular mom and the value that's predicted by the model. We square that up so that they're always positive, and then add them up over all of our mother-daughter pairs in our data set, and this is what we get. So this line here is the one that makes this number as small as it can possibly be. Now, if we didn't know anything about the mom's height, in other words, if we had no access to that information, then the best we could do in order to guess how tall a daughter would be is to is the mean. In other words, the mean height of daughters. And that mean we often write as sort of y with a little bar on top of it like that. So the bar is usually our shorthand for saying, ooh, that's a sample mean. And this is the total amount of error that we would get if we didn't know anything about the explanatory variable. In other words, if our line was just purely flat. So, and this reflects the idea of not knowing what the explanatory variable is because we're predicting exactly the same thing for every daughter, regardless of her mother's height, if we're using this dashed line here. So this is the total amount of error, the total sum squared residuals that we would get if we didn't know what the explanatory variable was. This is how much we got when we did know what the explanatory variable was. So we can see that sum of squares actually is smaller. So in other words, this sum of squared errors when we know the explanatory variable is smaller than when we don't. And the difference between those two numbers works out here. That is how much variability in the response variable can be explained or accounted for by the linear relationship between it and the explanatory variable. In other words, it is how much our error in guessing the height of daughters was reduced by gaining knowledge of the explanatory variable. In other words, by gaining knowledge of the mother's height. And we can then use the same trick that we saw with analysis of variance and say, well, this is equivalent to the between group sum of squares in analysis of variance. And so what we need to do to ask, well, okay, what proportion of variance in the response variable can be explained by this linear relationship with the explanatory variable? Well, we just divide that by the total amount of error that we would get if we didn't know what that explanatory variable was. And when we carry out that calculation here on the bottom left, we find that the height of the mom explains about 10% of the variability in the adult heights of women, their daughters. Now, here's the fun thing. R squared, the proportion of variance explained, is exactly equal to the square of the Pearson correlation coefficient. So this is the value of the Pearson correlation coefficient between mom's heights and daughter's heights, 0.314. Square that, and we get exactly the same value. In other words, if we know the correlation coefficient, we know the proportion of variance explained by the explanatory variable. And yeah, just to kind of emphasize that relationship again, we can write, and indeed a lot of statistical software will produce output that looks like this, where we have the sum of squares due to our explanatory variable, sum of squares error, that is to say sum of squares due to just typical sampling variability. And when we get a table like this, we can use it to figure out the proportion of variance explained by the explanatory variable. Now, to see this again in a new kind of more modern kind of practical setting, we're going to take a look at some data that came out of this study here, in which they were interested in the relationship between collegiate football experience and the different aspects of brain and cognitive outcomes. So the sample they had here was 50 NCAA Division I college football players. And among other things, what they did was scan the heads of those players using a high-resolution MRI, the same magnetic resonance imaging. And although they collected a lot of interesting response variables here, the response variable we're going to be interested in today is the total volume of a particular part of the brain called the hippocampus. And this is one of my favorite parts of the brain because it pertains to a lot of the research that I do, because the hippocampus is critical for the rapid formation and use of various kinds of associations. So it's important for forming associations between events and where they occur. Spatial memory is important for associations between events and when they occur, so memory for the time of an event, and also associations between elements of an event. In other words, the things that kind of pull together features of an event to form an episodic memory. So the hippocampus is critical for both forming and retrieving memories about our own experiences. And so, as you might imagine, this is a hugely critical function for this, these areas to serve. And our question is, does football experience have an effect on the anatomy of this critical brain region, the hippocampus? And so, although we won't be able to do our normal sort of class discussion today, unfortunately, but I will alight on this idea here so you can kind of take some time to think about it. Because this right here on the left shows the response variable, hippocampus volume, on the vertical axis, versus the explanatory variable, which in this case is numerical. It's the number of years spent playing football by each person in the study. So each point here represents one of those 50 football players, and we can see that some played football for maybe like 7 years, something like that. Some played for 18 by the time they were in there. And yeah, so I will kind of let you take a bit of time on your own to think about the following issues. So first, what does it look like the strength and direction of the relationship is based on this scatter plot? Does it seem like there's something going on there? Second, how confident would you be that there is a real systematic relationship between these two variables? So obviously, these don't lie strictly on a straight line, but maybe there's still something there, something going on. So how confident would you be in staking that claim? Another issue to think about is if you had to make a guess about the volume of someone's hippocampus based on years spent playing football, would you feel more certain in your guess if that person played 13 years, so in other words, if they were kind of right in the middle here of our data, or would you feel more certain if they had played 20 years or 3 years, something kind of way on the extremes, or maybe even beyond the range of data that we have? And again, we won't be able to do this, unfortunately, because we're not meeting in person. But you can imagine, maybe kind of coming up and drawing a line through these points that seems to you to best capture the relationship between, these two variables. Like I say, I'll let you kind of pause this and give a think to these different issues. And when you're ready, we can go to the next bit. All right, so what this graph shows is the same data, so the same points as we saw before, but this blue line here is the line of best fit. It is the result of doing linear regression, the line that minimizes the sum of squared errors between the observed hippocampus volumes of each player here and the volumes that are predicted by the line. And here is the equation of that line. So the intercept is 7,570 microliters, so that's the units here of our response variable. And here's the slope. So this is hippocampus volume as a function of years played. And the slope is negative 128. And because that line has a negative slope, that suggests that the volume of the hippocampus decreases for each additional year of football played. And this kind of little gray region here that you can see, this is something that a lot of modern statistical software will give us for free, has some interesting features, and that region basically contains the 95% plausible lines, 95% most plausible lines that would go through all of these data. And based on kind of the shape of that region, we can see that, okay, most of them also seem to have a negative slope. In other words, the region at the end is below the region at the beginning, suggesting that this negative slope is kind of a reliable trend. But of course, we still haven't gotten to the mechanics of this, so we still haven't seen, okay, how do we find those plausible lines? Second, how is it possible for us to rule out the possibility that there is no relationship? So this is going to be a kind of hypothesis test. And finally, we'll be interested again in looking at that R-squared thing. So how much can football experience explain these changes in hippocampus volume over time? Now, one final thing I'll note about this sort of interesting thing about this range of plausible lines, that the range kind of spreads out the farther we get from the center of our data. So it's sort of tightly constrained when we're near the middle of our data, but we get more and more uncertain as we go beyond the range of our data. And this is something that we talked about actually when we initially discussed linear regression, that extrapolation, that is to say predicting a value that's outside the range of the data that we've observed, is tricky business, and is not always something that we are either able to do or even that would be advisable to do. And that's reflected in the expansion of this gray region here, representing where we think most of those plausible lines are going to fall. Now, one way that we can find the set of those plausible lines that gave us that kind of interesting little gray region is to use bootstrapping. So this is something that we've seen before, and so one thing we can do then is simulate different possible data sets. So what we're going to do is use bootstrapping to simulate a whole bunch of imaginary data sets we could have gotten, assuming that our sample is representative of the population. And then for each of those simulated imaginary data sets, we find the best fitting line for that imaginary data. And then across simulations, we can look at the distribution of slopes for each of those best fitting lines. This gives us a sampling distribution for the slope. So let me just kind of now visualize for you a little bit of how that works. So here's one simulated data set from bootstrapping, and remember, with bootstrapping what we do is we take our original data and we basically treat it like those kind of big ping pong ball machines that they use to do lottery drawings. Each of these points becomes a ball in our machine. We jostle it up, pick one of those out, add that to our imaginary data set, put it back into the jar, shake it up again, pull out a new ball, add that to our imaginary data set, and keep doing that until we get the same number of people in our imaginary data as we had in our original data. So 50 in this case. So we keep doing that until we get 50 new people here, and you'll notice that some people do end up in our new imaginary data set, some people don't, so this point isn't here anymore. But then, with that imaginary data, we find the best fitting line. This is something we just use software to do. We're not going to do that by hand, but the best fitting line for this particular imaginary data set has a slope of 7140, or excuse me, an intercept of 7140 and a slope of minus 104, so it's negative again. Here's where that best fitting line for this imaginary data is. Here's another imaginary data set created by bootstrapping. Slope and intercept are not exactly the same, but they're not too different either. Here's one that maybe looks a little bit different from our original data. So you notice we only have 2 people in our original sample that have really long, that spent a really long time playing football, like 16 or 17 or 18 years, something like that. This particular imaginary data set happened not to include those people, and as a result, the slope actually is a little bit shallower for this imaginary data set. It's not as strong of a downward relationship as we got with our original data. But as I say, the interesting thing is that across, say, 10,000 or however many we want to do of these kind of bootstrapping resamples, we can make a histogram of the slopes that we got from fitting a line to each of those imaginary data sets. And that's what this is right here. This is our sampling distribution for the slope. And this green kind of colored region in the middle represents the 95% confidence interval for that slope. And in this case, I did 1,000 simulations of this, and the 95% confidence interval for that slope turned out to be minus 187 all the way up to minus 67.6. In other words, for each additional year of football played, we would expect someone to lose between 67.6 and 187 microliters of their hippocampus. In other words, for each additional year, that is the cost you pay in terms of the volume of this region of your brain that's important for forming and retaining memories. We can use that 95% confidence interval to make a 95% predictive interval. In other words, we can make an interval that represents how much we would expect things to change for a given person. So let's imagine that we have, say, a high schooler who's considering whether or not to play football in college. And assume that they would spend 4 years in college and play all 4 of those years. So how much of this student's hippocampus could he plausibly expect to lose over those 4 years? So we can express this as a 95% confidence interval, except now it's going to be a confidence interval for this prediction. How do we get that interval? Well, we take the 95% interval for the slope and multiply each of those numbers by 4. Why do we do that? Well, remember, the slope is how much we expect the response variable to change when the explanatory variable increases by just 1 unit. And so if we want to predict how much it's going to change when we increase it by 4 instead of 1, we multiply it by 4. And that's what we get here. So over 4 years, we would predict that the student would probably lose, not a guarantee, but would probably lose between 270 and 747 microliters of his hippocampus. And just to kind of give a sense of that, remember that someone who played no college football, so this is our intercept here, would have a hippocampal volume of about 7,500 microliters. So it's possible for this student, by playing 4 years of college, to lose about a tenth. So that is, say, 1/10 of the total volume of their hippocampus. Now, one other thing you'll notice from this is that because we're multiplying these numbers here, the bigger the difference in the explanatory variable, the wider the interval we're going to get. In other words, the more uncertainty we're going to get. So this is where we get that sort of fanning out that we saw with those kind of little gray regions before. The farther away we go, the bigger the change in the explanatory variable. That's going to magnify our uncertainty about the slope. But even though it magnifies our uncertainty about the range that the student may lose, it doesn't really change the direction. So we still would expect them to be losing hippocampal volume, which is a question of how much they lose. So that is the story for confidence intervals derived from simulation for linear regression. Now, we can also use random permutation, our other simulation method, to simulate possible data sets in which there is no relationship between the explanatory and response variables. This is exactly like what we did with analysis of variance, or when we were looking at differences between 2 independent samples. We just randomly permute them. So if there's no relationship between them, then the data should look the same, even if we randomly permute the values of the explanatory variable across our different cases in our data. So for each of those random permutations, we can do that, then find the best fitting line for each of those simulated data sets, just like we did with bootstrapping a few minutes ago. And across simulations, the distribution of slopes reflects how much we would expect that slope to vary, even if the null hypothesis were true. In other words, even if all the variability that's systematic were due to just sampling variability, differences in, differences between people that we would expect to see normally. So here's a couple of examples of doing that, and here's one of those simulated data sets created by random permutation, and up here is the equation of the best fitting line for that simulated data set, represented here, and this one happens to go up. Let's see, this one, all right, this one happens to go down, but not by very much. This one happens to go up again, although not by much. So you can see that this kind of corresponds with our intuition that, well, if there is no relationship between the two variables, then this line should be flat, and that's what the null hypothesis would predict. And when we say flat, what does that mean? Well, that literally means a zero slope. So we would expect, on average, if the null hypothesis were true, that most of the slopes we would see would be around zero. So this is the distribution of slopes we would expect to see if the null hypothesis were true. And this big red line here is the slope that we actually saw in our observed data. So across 1,000 of those simulations, across 1,000 random permutations of our data, none of those simulated data sets resulted in a slope that was at least as large in magnitude as what we observed. So that means that the simulation-based p-value is 0 out of 1,000, so 0. So if we go back, remember our research question is there a relationship between number of years playing football and hippocampus volume? So the null and alternative hypotheses that would correspond to that research question would say, well, okay, the null is that the slope equals 0. So in other words, the null is that there is no systematic relationship. So yeah, that's what would be true if the answer to this question was no. And the alternative is just that there is a relationship. So in this case, the slope is just whatever it is, we don't know, but it just, the alternative would say that it is not equal to 0. So based on this very low p-value here, we would reject the null hypothesis. We would say, nope, these data would be very unlikely if the null hypothesis were true, because these are the slopes that we would expect to see if the null were true. This is what we actually saw. It's way outside this distribution. And we would conclude that there is, in fact, a systematic relationship between years of football experience and hippocampus volume based on these data. Now, there is, of course, a mathematical model as well, not just simulation, for excuse me, for doing inference for linear regression. And in fact, the mathematical model for the slope in linear regression is based on our old friend, the t distribution. Now, the calculations involved are basically never done by hand. So what I'm going to run through for the next couple minutes is how to parse the output from statistical software that would do them for us, and we'll get more experience with this in our lab next week. So this is one example from the statistical software package R of what we would get by telling R to find the best fitting line describing the relationship between years played, and hippocampus volume. And you'll notice that, I mean, there's a bunch of stuff going on here, of course, but you'll see some maybe familiar looking things here in this kind of very computery looking table. So here, let me kind of pull out some of those things for us. So one thing that this table tells us, and this is again the sort of thing that most statistical software would give us, is, well, okay, if we wanted to find the estimated slope for the best fitting line, that's going to be in column that's often marked estimate or something like that, and we see okay, years is that the name of our explanatory variable, so we look at years estimate. Okay, then here we go. That's the slope of our best fitting line, minus 127.8. So that's what we saw before. Second, I mentioned that the mathematical model for testing the null hypothesis that the slope is equal to 0 is based on the t-distribution. And if we want to find the p-value that would result from that, we look in that same row of this table and we look, okay, there's a thing that kind of looks like a p-value. It's the probability of getting something that is bigger than a particular amount, and here it is. Often statistical software will also give us these little stars here that sort of guide the eye toward small p-values. And we see that from the simulation, 0 out of 1,000 simulations produced a slope that was at least as extreme as what we actually had. And according to the mathematical model, that p-value is indeed 0.0003, so very, very small indeed. Now, the proportion of variance explained is actually also embedded here in this output. It's a little bit harder to find, but it is listed down here. So we see here multiple r squared, and this is the proportion of variance in hippocampus volume that is explained by number of years spent playing football, and that works out to be 0.237. So that's this number down here. About 23.7% of the variance in hippocampus volume in the sample can be explained by number of years spent playing football. And we can also use this table to construct a confidence interval. And to do that, we would need the standard error and the number of degrees of freedom. So the standard error of the slope, in other words, how much we would expect the slope to vary from sample to sample, is usually a column here marked standard error, helpfully enough. And we look at that for the name of our explanatory variable, years, standard error. All right, it's about 33. And as I mentioned, we would then also need the number of degrees of freedom for the slope. And that is right here, it's 48. So the formula for that is that the number of degrees of freedom for a slope is sample size minus 2. It's not sample size minus 1 anymore, it's sample size minus 2. So we have 48 degrees of freedom because our sample had 50 people in it total. So let's see how we would actually use this mathematical model output to calculate a confidence interval for the slope in the same way that we used bootstrapping to do earlier. So we would first need to find a critical t-value based on the number of degrees of freedom that we have here. As I mentioned, the degrees of freedom for the slope are 2 less than the sample size, so n minus 2, which in this case is 48. And we can use our t-distribution calculator to find that the critical t-value for a 95% interval with 48 degrees of freedom is 2.01. And that's, our old friend here. So we see that right here. We say, put in degrees of freedom 48. Make sure that we've got 5% on the outside, because we want 95% on the inside. And here's our critical t-value. And the 95% confidence interval formula looks exactly like it would be for the mean or for a proportion. We have our point estimate plus or minus the critical value times the standard error. So the point estimate that we've got here is that's the estimate of the slope from our model, minus 128 more or less, plus or minus the critical t-value 2.01 times the standard error 33. And that gives us a 95% confidence interval of minus 195 up to about minus 61.5. And just as a reminder that, I'll let you think about this. Are you surprised that this interval is slightly wider than the 95% interval we got from bootstrapping? And to think about that, I'll just give you a hint to remember that we're using the T distribution, which has some interesting properties that differ from, say, the normal distribution. So that those properties may give us a hint about why this interval is slightly wider than we got from simulation. Now, there are, just like anytime we want to use a mathematical model for doing statistical inference, some conditions that need to be satisfied. On the one hand, the first condition is linearity. So in other words, when we make a scatter plot of the data, we should make sure that a line is actually a good description of the relationship between the explanatory and response variables. If it's not, then there's no point in testing the slope, because if a line doesn't really capture the relationship, then who cares what the slope of that line would be? It's not really meaningful. Second is our old friend, the independence condition, so each observation should be independent of the others. And note that this is actually violated when time is the explanatory variable if we're making multiple observations from the same person. So that actually does violate this independence assumption, and it becomes questionable then whether we can use a mathematical model for that kind of data. Another condition is what we call normal residuals, and in other words, the residuals should be distributed around the line of best fit in a roughly normal shaped way. In other words, there shouldn't be some extreme values that the line fails to fit. And finally, this is kind of related to this idea of normal residuals. We want to have equal variability, so residuals should have approximately the same degree of spread across the range of our explanatory variable. And yeah, so for example, this this line here and this line here and this line here, they all violate these two conditions here: normal residuals and equal variability. And we can see that kind of on the bottom graph where here the residuals are not evenly distributed across the range of the explanatory variable. Here they sort of fan out, so you get more and more noise, more and more error as you go. And here the error sort of fluctuates in a sort of seesaw pattern around the line. And if you see data like this, that suggests that there's probably some like cyclical trend, like maybe this would be something like seasons or days of the week, something like that, would lead to a relationship that had this kind of seesaw pattern. In that case, you'd want to have a model that accounted for that, which would not be a strictly linear model. And so here is just me kind of labeling all of these different violations of these different assumptions here. And if you ever see data that look kind of like these, well, you probably shouldn't be using a mathematical model for doing inference about linear regression. And yeah, so that brings us to the end of our kind of tour of doing inference with linear regression. And as a reminder, we've got a new, this is our very last learning check that's posted as of 1 p.m. on the November 20th, and it'll be due by starter class next Wednesday, so not Monday, but Wednesday. What is due by next Monday is just to make sure you get the questions from our analysis of variance lab from last week. Make sure those are handed in by then. And we're all the way up to our very last chapter, chapter 18. So with that said, thank you very much for your flexibility. Again, sorry that I'm pretty under the weather here, and don't want to expose you to that. And I hope you all have a good Thanksgiving holiday, and I look forward to seeing you when we get back.